Good morning, greeting, and warm welcome to all. I, Astha Parashar.
I, Anisha Khose, welcome you all in the behalf of IPS Academy Institute of Engineering and Science. Welcome to day 4th of our discussion of 6-day event of Faculty Development Program on Design and Simulation of Next Generation Semiconductor Device and its application for biosensing. As we move forward, we have among us our chief guest, Dr. Ambika Prasad Shah, sir.
Sir is currently working as an assistant professor in Electrical Engineering Department of Indian Institution of Technology, Jammu, India. He was also the visiting professor at the University of Virginia, USA. Sir received PhD degree from Electrical Engineering Department, IIT Indore. He has authored more than 90 research papers in peer-reviewed international journals and conferences. Also, Sir is a guest editor of Springer Elsevier Journals, fellow of IETE, and senior member of IEEE. His current research interests including reliability analysis of digital circuits, designs of reliability, fault-tolerant circuits, reliability modeling circuits, and hardware security primitives.
Now, I request Professor Rupesh Dubey sir to kindly felicitate our chief guest Dr. Ambika Prasad Shah sir with sampling gesture symbolizing our gratitude for his presence and wisdom. Thank you, sir.
Thank you so much.
Now, I request Dr. Ambika Prasad Shah sir to uphold the dance. Welcome, sir.
Actually, thank you so much, IPS Academy and IES especially, for inviting me for the talk, especially on this FDP program on design and simulation of next generation semiconductor devices and its application for biosensing. Basically, I will be talking about what are the reliability challenges, what are the like how to measure the quality of any integrated circuits, and basically I'm not here to present what kind of work we are doing, because see, if I will be showing like what kind of work I am doing, maybe it's not useful for you. I will be talking about what kind of problems are there, how you can deal with it, and what are the different challenges and what are the solution of those challenges. So this is the basic motivation of this particular talk. So the major thing that I will be considering about integrated circuit reliability and its quality, how to maintain the reliability, especially with the skill technology, the reliability makes some sense, like because with the skill technology, reliability of any circuit is okay. So reliability is really very important to consider, especially for the skill technology. So before I start discussing what kind of challenges we have, let me talk about what kind of things I will be considering about. The first thing I will talk about the introduction of the different issues. Then I will talk about what different reliability issues are, like PVT variations, bias temperature instability, hot carrier injection, TDDB, and the aging effects. And then I will talk about, especially if I am going to use my circuit for space applications or in radiation hardened environments or radiation environments. So what are those challenges, how to overcome those problems, and what are the way how to investigate those things. So this is the thing which I am going to consider in the soft error one. And then I will talk about what are the different near term like problems, like currently what kind of problems that we need to address, and what kind of problems may come after 5 years, especially in reliability domain of any circuits. So this topic is really very important because we keep on decreasing the size of transistors. Initially there was 500 micrometer transistors. Now people have started working on 1 micrometer transistor sizing. So this much of huge difference is not that much easy. If you scale down the technology, definitely reliability is an important concern that need to be considered. So this is the motivation behind these things, and these are the few reliability challenges which can affect the performance of those circuits. Okay. Yeah, before I start, this is my team. Currently I have 12 students who are working with me in my lab. Most of them are doing PhD and masters. Yeah, I think 8 are PhD and some of them are the masters. Yeah, these are some of the lab infrastructure. Currently, yeah, 7 PhD and 7 MTech and BTech students. I have some decent fund to run my lab, and the major software which are needed for VLSI that we have, especially that was funded from the Chip to Starter program from MIT. Okay. This is brief work which I am doing uh, in my lab. Basically, most of the domains which I am working on is related to the reliability and the security. So if you talk about the semiconductor industry, there are two things that need to be considered. The first thing is the reliability, and the second one is the security. Because nowadays we have all the information which is in the form of virtual, right? So in the form of digital form. So that information need to be secure enough. Whatever the system we are using, either mobile or any computer or any laptop, that need to be secure, because most of the information I stored there. So maybe I can relate something how I can connect reliability with the security, because these two are the part of resilience, system resilience or circuit resilience, and they are interrelated. If some circuit is reliable enough, so that's fine, because that will operate properly. But if it is unreliable, definitely we can use it. So this is very funny thing about semiconductor research is, like, if any circuit is reliable, that's perfectly fine, we can use it for our applications. But if it is not reliable, I can use it for some other purpose. So it's not like whatever work you have done is not worth, like it can be used for other applications. Ultimately it depends on what kind of applications you are considering. So yeah, some of them are related to the reliability and some of them are related to the security. So we talk about side channel attack, we can talk about hardware security primitives, how we can maintain the security of all the circuits, and of course how we can make the secure cyber physical system. So these are some of the domain in which we are working on. Yeah, there are some of the glimpse of our research work which we are working on, like from NBTI to radiation hardening, then side channel attack, which is one of the part of security concern. In-memory computing nowadays becomes very important thing, because if you talk about high performance computing, in that case, von Neumann architecture may not be sufficient enough. So you need to talk about near memory or in-memory computing that increase the performance or reduce the latency. So that's very important thing that need to be considered. Second thing is, like, if you talk about analog circuits designing, like any ADC or other kind of things. So ring amplifier is one of the candidate to design a ADC with low power and high performances. So this is very important. Like this kind of circuit, people have started working on only like last 5 to 6 years only. So this is very new domain where the people are started exploring the things, and we have done a lot of work in this direction. So this is really very good topic, especially for those who want to work in the analog side in the circuit side. And the last one is the hardware security. Of course, the physically unclonable function, how you can generate the secret key for the encryption purpose. So these are some of the work which we are working on. Yeah, these are some of the collaborations. Now let us start the main things which we need to discuss here. As we know that with the technology scaling, we can see here even before, I think it is visible from back, right? Okay, so if you can see here, the minimum which I have considered in 2005, it was 5.6, it was 90 nanometer. But before that, we have other older technologies which are 500 micrometer and 500 nanometer, and then 135, 180 nanometer, 350 nanometer. Then it comes to 90 nanometer and 65 and so on. So all these miniaturization of the devices up to this 5 nanometer, these all are the material based. So if we change the material, if we change the dimension of those source, drain and other things, and if you try to align all those things properly, then you can achieve up to this 5 nanometer. But because we know that any charged particle may take some time to travel from source to drain, because ultimately there are 3 terminals, source, drain and gate terminal, and of course there is a body terminal. But if I am applying some potential at the gate side in any of the MOSFET, it will start operating, and based on the potential at source and drain, it can transfer the charge carrier or it can stop the charge carrier. It depends on the potentials. But there should be at least some distance between source and drain so that the charge particle can travel. If we keep on reducing those things, in that case, might be even below 2 nanometer, it will not be sufficient in the conventional kind of miniaturization. So the different kind of technologies then can come, and those technologies are the photonics integrated circuit. These are one of the domain where people can consider. So here, like, instead of normal charge particle transition from source to drain or two terminals, you need to consider some photonics, like photons need to be traveled from one node to another node for the communication purpose. So this is one of the domain. The second domain that people can explore is the neuromorphic computing, especially for now you know that in human body there are lots of neurons, and if you want to replicate the model of your mind or your human body, you need to consider lots of computation, because we have lots of neurons, and to connect all those things, so neuromorphic computing required lot of computation, and that required very fast computation, because ultimately, and for that you need to come up with a device which is very small, and that takes very less time to take the decision. Another one is the quantum technology, which is really very important to consider, because I was talking about up to 2 nanometer. This is perfectly fine. We can manage with the normal semiconductor materials, but less than 2 nanometer, quantum technology is one of the new technologies that can be considered, where they talk about how a quantum movement, and based on their polarity it can be decided. So if the quantum dots are positive polarized, so we can consider it as a logic 1, and if it is negative polarized, we can consider it as logic 0. So based on the polarization of the quantum dot, single quantum dot, the decision can be taken. So this is the next technology that is coming to be in picture in next 5 to 10 years. As of now, there is no chip has been fabricated on this, but yes, you can consider in next 5 years we will have some chips which is based on the quantum technology. So might be I can help someone who really wanted to work in the quantum technology. We have done some work in the quantum dots, and we have designed some of the circuits, and it's very easy. You don't need to purchase costly softwares. There is always there is available free softwares. You can use it and you can design your circuit, and it's easily doable. So this is one of the techniques. And of course, these all the technologies which I am talking about, these are all the silicon based. So other than the silicon, there is other technology that can be considered, because it ultimately depends on the material, which kind of material I am using to design our devices. So these are some of the way where the people can work. People can work on these technologies where normal material based miniaturization is done. But other than this, if you want to really improve the performances, if you want to really come up with the processor which can be useful for the high performance computation, in that case you need to come up with all these technologies. Okay, so this is simple scaling era. So I think this is the decent motivation about what kind of work can be done in different technologies, and what are the different technologies that can be considered. Yes, so let us talk about the simple miniaturization or simple scaling down the technologies. So initially, if we talk about simple MOSFET structure, we have some source, drain and gate, and whatever the doping concentration is there, if I want to reduce the size, so it's not just reduce the distance between source and drain, reduce the size of this diffusion, reduce the size of this capacitance, all those things. It's not only these things. We have to change the concentration as well. So after scaling, the size will be reduced. Of course, the doping concentration will also be changed, so that I can maintain the performance. It's not just to reduce the size and you will get the performance. If you want to maintain the performance, definitely you need to change the doping concentration as well. Okay, so basically there are it's really very important thing, like in each next technology generation means, like if we can see here in the previous one, 90 to 65, 65 to 40, 45, 40 to 28, these are the next technology generation for each stages, right? So for each next technology generation, the oxide thickness is reduced by 30%. This is really very important to understand, and these are one of the reason how the reliability comes into the picture. Okay, so for each next technology, the 30% reduction in oxide thickness play a major role to decide to check the reliability of any MOSFET or any circuit. Okay, so if the oxide thickness is reducing, the PVD variations becomes the biggest design challenge at the scale technology. So I will be talking about all what these reliability challenges are and how it can be overcome. Okay, so reliability and variability becomes really a very serious challenge that need to be considered for the scale technologies. So ultimately at the scale technology, two things need to be considered. One is the excessive leakage power dissipation, because at the scale technology, power dissipation becomes really a challenge. Okay, so if you want to use your circuit, your chip for battery operated devices, definitely power consumption should be as small as possible, so that you can run your system for the longer. Okay, so you need to consider how I can reduce this leakage power dissipation. Ultimately, leakage power dissipation lead overall power dissipation of the chip. Okay, so that can be designed with the proper topologies, proper methodology, and with the help of those methodology, I can reduce the leakage power, and ultimately overall power dissipation of the chip will be reduced. But other than leakage power, like considering different topologies, this is really very important, where I need to talk about, of course, we have reduced the leakage power, we have reduced the power, but whatever the circuit we have designed, whether that circuit is really reliable or not, can it be used for applications where reliability is very important, especially like space applications, like biomedical applications. In biomedical application, if there is some fault, there is some change because of unreliability of the devices, might be the whole system can fail, and we can lose one life. Okay, so because of that, reliability need to be tested for all the devices, all the circuits, and that becomes really a challenge. Okay, so we'll talk about how we can do that. So if I can broadly discuss about the reliability, PVT is one of the problem that can be considered. PVT is nothing but process voltage and temperature variation. Voltage and temperature is perfectly fine, because if there is fluctuation in the voltage, that we can call it the voltage variations. If there is fluctuation in the operating temperature, that we can call it the temperature variation. But process variation is really very important. Let us assume I want to design a chip, and let us talk about simple circuit. Let us assume I have a circuit having 10 transistors. Okay, and I am considering, while simulating or while designing, all the 10 transistors are identical. Okay, so while simulating, we are considering all the transistors are same, but in reality, while fabricating, you cannot fabricate two transistors identical enough. There will be some variability, there will be some mismatch, because there is a process to fabricate any devices, and for the lithography purpose, still 130 nanometer wavelength of light is being used for the lithography. Even the technology is either older than 130 nanometer or less than 130 nanometer, still 130 nanometer wavelength of light is being used. So if the technology is like, if the transistor size is more than 130 nanometer, then perfectly fine. Let us assume I am considering 180 nanometer technology. So 130 nanometer wavelength of light is sufficient. That is fine. But if I am using 65 nanometer model to develop our circuit, in that case, still I am using 135, then process variability will come. Okay. So ultimately, the process variability is because of unidentical fabrication of the devices, because of the change in the wavelength. Okay, because the wavelength of light is 135 and the technology is 65 or even less than that, that will create a mismatch, and because of that, variability comes. Okay, now the problem is, nothing is how we can overcome those things. Okay, so here I will talk about how we can maintain the process variability, temperature variability, and the PVT variations. These all are whatever the things which we have seen here, PVT variations, these are the time independent one. Okay, time independent ones means while fabricating any circuit, this kind of problem may come, and if this kind of if any fluctuations is there, like in voltage and temperature, that can create a problem. But some of the reliability issues that comes with the time. Let us assume you must have observed, if you purchase any gadget like mobile phone, now the performance is very fine, it can operate very faster, but with the time it start lagging. This happens with the mobile phones, and this happens with every electronic gadget. So what is the reason behind that? The only reason is some of the temporal variations. Temporal variations means these are some of the variations which can affect the performance of your circuit with the time. Initially there was no effect of this kind of variations, but with the time this kind of problem comes, and those problems are bias temperature instability, hot carrier injection, and time dependent dielectric breakdown. What these problems are and how to overcome these problems, what are the benefit of these problems? Of course, whatever the problems we will discuss here may give some benefit and people can think for their research. Okay, so these are the three problems which are time dependent, and with the time this problem comes. Okay, so I will talk about what those problems are. The next and the very important problem is the soft error. What is a soft error? If I have designed certain circuits, okay, and each circuit has certain nodes, storage, let us assume I have a memory, okay. In memory, I am storing some data, okay, but at each storage node, there is a fixed charge that can be stored, okay, and if some high energy particle strike at that node, might be that charge can change its status and might be the information can flip. Let me repeat it again what is happening. Let us assume I have a memory. In a memory, I am storing some data at certain nodes, okay, and if some high energy particle strike, especially in the space applications or in nuclear environments where the probability of high energy particles are very high, okay, and those high energy particle can strike at the sensitive nodes where I have stored the data, and at those sensitive nodes might be the charge whatever I have stored that may flip, that may change its polarity, and if it changes its polarity, might be the logic will be changed. So this kind of problems we can call it the soft error. Soft error is really important, especially if I am trying to design a chip for nuclear environments or for the space applications. Okay, so how to overcome these problems I can talk about. So I think I have given sufficient introduction about different reliability challenges. So let us talk about one thing I was talking about at the beginning, like the circuit and system resilience is really very important. Resilience means there are two things that can be considered. One is the reliability and the second one is the security. Okay, I was also talking about if your circuit is not reliable enough, that can be used for some other purpose as well. Okay, so this is very funny statement, but this is true. Okay, so yeah, this is really very important. If we talk about the circuit and system resilience, there are three domains in the circuit and system resilience. One is the integrity, second one is the availability, and the third one is the confidentiality. Okay, here you can see there are two things. This, like in the pink boxes, all these are the reliability challenges. Okay, reliability challenges means there could be some internal interference, there could be some process variations. What is the process variation I can talk about later on. There may be some environmental noise that can affect. So these are some of the reliability challenges that can create the question mark on the integrity of the circuit. Okay, so if there is a less variability, less process variations, might be this can lead to the integrity of the circuit. Similarly, if we talk about, there could be some possibility of transient fault, there could be possibility of some intermittent fault, or there could be some permanent fault. And if there is some possibility of faults, so this can create a problem in this domain, which is the availability. Similarly, if we talk about, there is a hardware tampering. Hardware tampering means, suppose I have developed some chip and intentionally I am changing the logic, intentionally I am changing the circuits, I am tempering the things. So this kind of problem, security threat, we can call it the hardware tampering. Okay, so this is also one of the things. Next one can be the accelerated aging. Okay, and accelerated aging is one of the things that can problem. Second one can be fault injection. So these three are the security concern, and these two are the reliability concern. Means while designing any system, while designing any circuit, the system should be secure enough and it should be reliable enough as well. So both can be considered. Okay, this is a basic classification of different reliability challenges, reliability failures, mechanisms. I have touched few of the things which I am going to talk about in more detail. I was just discussing about there are two kind of reliability concern. One is the time zero and the second one is time dependent. Time zero means time independent one, where we talked about PBT variations. So these all are like local and the global variations, front end, back end, RDF, LER, OTV. I will talk about all those things, don't worry. These all are the reliability concern, which is the time independent one. Okay, if you have any question in between, you can ask, right? It's not like and these are some of the concern which are the time dependent. So let us talk about all these things one by one. The first reliability concern is the inter-die variations. What is the inter-die variations? Have you seen the dia before? How the wafer looks like? Okay, so basically, wafer is nothing but a silicon sheet where we used to fabricate the chips, right? And if we have multiple chips on the same wafer, so we need to dice it, and those we can call it the dia. Okay, so basically there are two kind of variability. One is in a single dia there may be different kind of transistors, and independent variability of the individual transistor on a single chip is one of the problem. And the second problem is on a single wafer, if I have multiple dia, even I have replicated them, still there is a variation. There is a change in those dias. So this kind of problem we can call it the global variations. Okay. So basically, intra-dia means in a single chip, if I have two identical transistors, and after fabrication, if both the transistors are not identical enough, then these kind of variations we can call it the intra-dia variations. Okay, let me repeat it again. Intra-dia means while simulating, while designing, if both the transistors are identical, but after fabrication, if they are not performing equally, then this kind of variability we can call it the intra-dia variations. What is the inter-dia variation? Inter-dia variations means like this is what is a lot. Lot is nothing but this is silicon ingot, and you have to cut like a slice, like a bread, and those becomes a wafer. Okay, so on a single wafer, like on a single lot, you can have multiple wafer. So if there is a variability between two wafers, so this is what we can call it the wafer to wafer variations. Even though we have sliced them from the single ingot, but there is a change in the performance of between two different wafers, so we can call it wafer to wafer variation. Other than this, if like, so this is like this one, and let us assume in a single wafer I have cut multiple dias, and if there is a variation in each dia in the same wafer, so this kind of problem we can also call it a dia to dia variation. So if the variability is independent of a single chip, single functional chip, then we can call it the inter one, and if the variability in a single chip for a particular application, then we can call it the intra-dia. Yes.
So it is after fabrication.
Yes, of course. After fabrication, see all these problems like while simulating, while designing, we have designed identical one, but maybe after fabrication there is challenges, because I just talk about the light for the lithography, which like the wavelength of light which I am using is still 135 nanometer. And if I am using, let us assume 65 nanometer, there is a mismatch in the wavelength, so that can create a variability.
So it can be used or not then?
It can be used, but we need to come up with certain techniques that can improve the reliability. So how to improve it, I will tell you. Yeah, so other than these things, like while checking the performance of any circuit, two things are really very important. One thing is the power performance, and the second thing is the speed performance. Ultimately, for any portable device or for any electronic gadget, either I need to consider like my mobile should be fast enough so that I can operate my task immediately, and the second thing is I must have sufficient power backup so that I can use it for longer. Okay, so these two are the things that can be considered. But while simulating, if I have given certain, let us assume I want to make a chip for this mobile applications, and for this mobile application I will have certain specifications like this much of power I need, this much of delay may be needed, okay, and all these like these many of transistors may be needed, this much of reliability can be sufficient for this particular application. So we have decided the parameter, we have decided the specifications. Out of those specifications, if I have to check whether, because ultimately reliability is going to come, okay, you cannot avoid it because you are using the lower technologies. If you cannot avoid it, so you need to come up with certain window, up to what window I can manage if there is unreliability in any circuit. So what is the range? What is the range which can be considered as a reliable one? Okay, so there should be some tolerance. We cannot stick to 100%, right? So there should be some tolerance, like if I need, let us assume 1 microwatt power, so might be 9 microwatt to 11 microwatt will be sufficient. So I need to create certain window which will be sufficient for my applications. So this spice box gives you the information like whether my circuit is within that window or not. So I have two major concerns that can be considered. One is the power one and the second one is the delay. Okay. So basically there are 5 process corners which are used to test your circuit. Okay. 5 process corners means fast, fast, slow, slow, fast, slow, slow, fast, and typical, typical. What is the difference between these things? Can I lock it? There's no lock. Okay. So, because it disturbs me, right? So, so basically there are 5 process corners to check the performance of your circuit. Process corners means what? Ultimately, for a particular applications in a design library, you can have multiple property transistors. There could be some transistors having the standard threshold voltage. There could be some transistor which can be the threshold voltage having lower than the standard one, and there are some transistors which can be higher than the standard one. So we can call them HVT, LVT, and the SVT. HVT means higher threshold voltage, LVT means lower threshold voltage, and SVT means standard threshold voltage. Generally, we test our circuit, we try to design our circuit considering the typical where both the transistor threshold voltages are standard one. Okay, moderate one. But there are some corners, because see, if I have a circuit, I can go into the extreme lower side or extreme higher side where we have certain limits. So to check all those things, I can consider the fast. One very important relation is, if the threshold voltage of any transistor reduces, the leakage power dissipation increases. This is one of the key relation that we can consider. Means the threshold voltage is like the power dissipation is inversely proportional to the threshold voltage. Second thing that I can consider is the delay of any circuit is directly proportional to the delay. So delay and the power dissipation are inversely proportional to each other. Okay. So now I just told you, if the threshold voltage of transistor is less, then the power dissipation will be higher. Okay. So let us try to see what is happening here. Fast simply indicates if the threshold voltage of both the NMOS and PMOS transistors are smaller, then the power dissipation will be maximum. And I just told you the power dissipation will be higher if the threshold voltage is lower. So if my circuit, so let us assume if I am operating my circuit at fast process corner and I am getting some power, so because at the fast process corner I will get maximum power dissipation, and if that power dissipation is within my window, then I can tell, okay, even after operating with this extreme limit, I am getting decent power dissipation which is sufficient for my requirements. So for power specification judgment, for power specification check, we need to test our circuit at this corner, which is the fast process corner. Okay, so so ultimately with the lower threshold voltage, if I am getting some decent power, and with that decent power, if it is fine, if it is matching within my window, so we can say, okay, this passed the power performance. Now I have one more performance that can be considered, which is the speed performance. Because ultimately whatever the circuit I am designing, that must have certain limit, like what should be the minimum speed that is needed. Okay, so because if I am increasing the threshold voltage, I just told you, with the increase the threshold voltage, delay increases. Okay, so if I want to check my circuit for the delay performances, I can check this slow one. Slow means both NMOS and PMOS transistors are having higher threshold voltage, and that will give maximum delay. And if that maximum delay is within my window, so I can say, okay, the speed specification is also matching as per my requirements. So this particular process corner is really very important if I want to check the power and the delay specification of any circuit. So and this is one of the things that can be considered for the reliability concern. Like this kind of reliability test is needed for understanding the power specification and the speed specification. Okay, and yes, there are two more corners. If there is some mismatch in one of the transistor and there is no mismatch in the second one, so I can check this one and vice versa. Because ultimately after fabrication, the threshold voltage degrades, the threshold voltage changes. So if there is only one change, like in only one transistor it is changing, so I can check this one and this one. So ultimately these are the balanced one, these three are the balanced one, because the changes are happening in both PMOS and NMOS transistors, but these are the unbalanced one, where one is fast, second one is slow, and here one is slow and second one is fast. But in these three, either they are fast, either they are slow, or they are standard one. Okay? Yeah.
Suppose at the edging, what will be the effect of threshold voltage?
Yeah, I am coming to that point. So these all are the normal time 0, 1. I am just coming to the BTI, that I can tell you like what is the aging effect and how it can impact, and definitely there is some benefit of it. Okay, so and that can motivate us to do research, especially in the NBTI domain. So that next, after 2 slides I will come to that point. Okay, so yeah, let us talk about the second one, is the interdia. Yeah, I was talking about oxide thickness variation. What is this oxide thickness variation? So how much time I have spent? So accordingly I need to manage. Huh? Okay, I need to finish by 12, right? Okay, and 14 slide. Okay, fine. So the oxide thickness, what is the oxide thickness variation actually? Oxide thickness variation means, let us assume I'm fabricating one MOSFET. Can I write somewhere? It is possible. So might be I can. Yeah, that's fine. Okay. So let us assume I have certain. Let us assume MOSFET. Yeah, that's fine. It will work. Okay, great. And this is nothing but, this is, we are calling it the oxide. Okay, this is typical MOSFET which we used to fabricate, right? Where we have some silicon substrate. If it is N-type MOSFET, so this will be N plus, this will be N plus, and this will be type P-type substrate. Okay. What is the OTV? Ultimately, if I try to miniaturize the transistor or reduce the size of transistor, what is happening? At the beginning we have seen, we need to reduce the distance between source and drain. We need to reduce the size of this one. We need to reduce the size, depth of this one. You need to change the doping concentration of this one. Okay, you need to change the doping concentration of this one as well. And we also need to change the oxide thickness as well. Okay, oxide thickness will be changed. Okay, so what happens? Let us assume I have a transistor and I am designing that transistor at 100 nanometer. Okay, and let us assume 100 nanometer is the transistor size, and out of that let us consider I have 10 nanometer oxide thickness, TOX. Okay, let us assume TOX is nothing but 10 nanometer. For example, I am changing the size, or I am reducing the size of this MOSFET from 100 nanometer to, let us assume, 10 nanometer. And accordingly, let us assume I have managed in a such a way that I can make the oxide thickness of 1 nanometer. Okay, simple mathematics I am doing. I am not going into more complex. Okay, initial size of transistor was 100 nanometer. Now oxide thickness is 10. The changed size of transistor is 10, and I am changing to 1 nanometer. Now, because see, ultimately how we oxidize the layer, ultimately because like there is a process which we call it the oxidation. Okay, oxidation is the process that oxidize, and I can create the oxide layer at the top of silicon. Okay, and that thickness is decided like how much thickness I need, but it is not necessary. Whatever the thickness I need, that will be 100% same. Okay, let us assume I wanted 10 nanometer, but there may be some 20% or 5% variation on that. And on a whole substrate, let us assume, if you can see the 3-dimensional view of this one, so might be you can visualize on the whole side. Yeah, this is one of the depth. Okay, so the thickness of oxide may not be uniform for whole device. There may be some variation, because I cannot get 100% accuracy to make the oxidation, to create the oxide layer, and that will be uniform throughout the device. Okay, so let us assume there is a 10% or let us assume there is some 0.5 nanometer variation throughout the surface. Okay, so let us assume 0.5 nanometer variation is there. So what will happen? The oxide thickness can be 9.5 nanometer to 10.5 nanometer. Okay, so if you can see here, the variation is plus minus 0.5 nanometer, and still this is sufficient enough. I'm getting decent thickness so that the device can work properly. Now let us talk about this one. Because I am using the similar kind of oxidation process, if there is a variation of 0.5 nanometer in this oxide, what will happen? If you can see here, the oxide thickness will change from 0.5 nanometer to 1.5 nanometer. Now you can see here, the change is plus minus 50% here. And here the change is only 5%. So only 5% variation is there. Here the 50% variation is there, even though the oxide thickness variability is remain same. So this kind of problem may come because, so at the lower technology, this oxide thickness variation create really a problem. Okay, so this is one of the concerns that need to be considered. How I can go back? So this kind of variation, we can call it the oxide thickness variation, and this is one of the problem that can be handled properly. Okay. Second problem is the random dopant fluctuation. Random dopant fluctuation is, of course, because to create source and drain region, I need to dope. Okay, and if I need to dope them, so if let us assume the initial doping concentration was 1 atom per 1000 particles, and the next one is like if I'm reducing the size, so overall doping concentration will be different, and if I'm using the same ratio with the lower size, might be doping concentration will be different. Okay, so random doping concentration gives you the idea. If there is a variation, let us assume I have 1000 dopant in the source side and drain side. This is simple, just for a calculation purpose. I have a source side and drain side. Let us assume on the source side I have 1000 dopant, okay, and on the drain side I have 1000 dopants. There may be possibility of number of dopants variations. Let us assume there is a variation of 50 dopants. So 950 dopants and 1050 dopants is possible. Now, if I reduce the technology, the doping number of dopants are also reduced. And if number of dopants are reduced, and if the variation is remains same, let us assume for the newer technology only 100 dopants are there in the source and drain side, and if there is variation of 50 and plus minus 50 dopants, then again the number of dopant will change drastically and the performance will change. So this kind of variability we can call it the random dopant fluctuation. Okay, and this is one of the things that create a problem in the things. The third one is line edge roughness and the line width roughness. What is the line edge roughness? Ideally, let us assume I am trying to design this kind of device. It is fine, right? So accordingly, I can manage the things. So let us assume I am trying to design this kind of device, but I just told you we are using different kind of wavelength of light for the lithography purpose. Might be you will not be able to etch them properly, just like we have seen how the PCB is fabricated, right? We are doing photo masking, then we are doing lithography, then we are etching them, okay, with some chemicals. But whatever the pattern we have drawn in the software, we cannot get the same pattern. There may be some less thickness, there may be some more thickness, and there may be some corner may be etched, there may be some corner which are not etched as per my design. So these kind of problems, so let us assume I wanted to design this kind of device, but after fabrication might be I can get certain variation like this. Ultimately, the process is similar, just like how we do for the PCB one. Okay, so we will get this kind of variation. So this kind of variation we can call it the line width roughness. So if I am not getting uniform width throughout the channel length, then this kind of variation we can call it a line width roughness, and this can create the problem in the performance. This is one of the reliability challenge. Similarly, line edge roughness means what? Of course, edges are also not fine here. But if we can closely look into this figure, the width is remains same throughout the length, but the edges are not same. Okay, so this kind of things we can call it the line edge roughness, and this is what we call a line width roughness. Width is not uniform here. Here width is uniform, but there is certain variation in the edges at the line. Okay, so these problems are because of the lithography process. Okay, so how much variation is tolerable? That is really very important to consider. Next and very important. Next one, if we can talk about the supply and the temperature variations. This is what I already told you. Like the supply voltage is really related with the delay of the circuit, and this is the typical relation between supply voltage and the delay. Okay, and if I reduce the supply, then delay will be higher, and if I increase the supply, delay will be lower. But ultimately, the power dissipation of any chip is also depends on the supply voltage. If I want to reduce the power, we know that dynamic power dissipation formula is nothing but FCV square, right? Where V square is the supply voltage. So the supply voltage directly play a major role how much power this circuit will dissipate. Okay, so if I can reduce the supply voltage, definitely I can reduce the power dissipation, but it will also lead to increase the delay. Okay, if it will increase to lead the delay, might be after certain supply voltage, you will get a decent delay that may not fulfill your delay requirements or the timing requirements. Okay, so that is really very important, which can be considered here. So I need to come up with some optimum supply voltage which is sufficient to fulfill the delay requirements and which is also sufficient to fulfill the power requirements. And to consider this thing, one of the parameters that can be considered, and we can call it the power delay product. We must have heard this term before. Power delay product gives you the idea about how much is the minimum power that is sufficient for my application, how much is the minimum delay that is needed for my requirements. And if we try to consider these two things, because if I will try to reduce one thing, second one will be increased, and the vice versa. So we need to balance between these two. So to balance these two, we need to consider power delay product. Okay, so power delay product gives you one of the figure of merit that decides how good your circuit is. Other than this power delay product, one more thing can be considered, which we can call it the energy delay product. Energy delay product gives you the idea how much energy is required to drive that circuit and how much delay we have. So considering these two things, energy and delay, there is a second parameter that can be considered to check the reliability or the performance metric. We can call it the energy delay product. Okay, so PDP and EDP are the important thing that can be considered here. I think there is some mismatch in the color. I think it is not visible. There are some other colors, like green and blue was there, but I think white is not coming. Don't worry. This is, I'm just trying to tell you the temperature variations. What is the temperature variation? If you can see here, let me give you some brief idea about what is the variability and the temperature variability. Temperature variability is nothing but if I have fabricated some chip, in a single chip, there may be different modules at different places. Let us assume this is the single chip, and in this single chip, let us assume I have here some controller which is processing all the time. Here I have certain memory which is storing the data, and that may require whenever it is needed. We'll fetch the information, we'll fetch the data whenever it is needed. There are certain module, let us assume Bluetooth connection module. There may be some GPS module. I'm just giving simple example. Some of the module may work all the time, and some of the module may not work all the time. This may be possible. In our whole, if you can check our mobile, internet is on all the time. So that module is on all the time, but Bluetooth we rarely use. So that module is not used. So what happens? If the switching of any logic is happening like frequently, so there may be switching from 0 to 1. Energy charge and discharge will be there. Charging and discharging may lead to some temperature variability, because if there is some charging and discharging, there is some change in the logic, activity factor is higher, then the temperature of that module may be higher than the other one. Is this fine? So temperature of a module depends on what is the activity factor of that module. So activity factor decides how I am going to use it, what are the models which are frequently used. So the activity factor will be higher, and if activity factor will be higher, then the hot spot will be created, means the temperature of that module will be higher. So this module may, the temperature of this module may be higher, temperature of the other module may be lower. So whatever the performance I have decided before, might be it will be changed for certain modules, and this kind of variability we can call it the temperature variation. So while designing any circuit, I need to check how much minimum temperature and the maximum temperature it can sustain, and within my requirements, within my limit. Okay, so while designing, this need to be investigated, and of course this depends on your applications. Let us assume I am designing my chip for my mobile phone. The minimum temperature it could be 0 or so, but maximum temperature it could be 50. Your mobile cannot hit more than 50, right? So I need to test within that window. But if I am using my chip for, let us assume, for a space where the temperature will be different, where maybe it can be extreme higher or lower, so I need to test at those temperatures. So this is really very important to consider, like whether your circuit is robust against temperature variation or not. Okay, yeah, so workload, if workload is increasing, switching activity will be increased, power dissipation will increase, that will generate the heat, and ultimately the temperature of that particular module may increase a lot. Okay, so that can create the things. Yeah, these are some interrelation between, if I have a low process variations, and these are some relations. So I'm quickly moving because I have to show different things. Voltage and temperature relation with the delay, this is the given. Yeah, this is important which you asked. Okay, let us talk about this BTI, what this bias temperature instability is. What happens? Because ultimately, I just told you in the previous diagram, like if I have to create a MOSFET, what I need to do? I have a substrate, I will have some source, and I will have some drain, and I need to oxidize to create the oxide layer, and then I need to have some gate terminal, which is a polysilicon. Okay, so these are the typical process that while fabricating any MOSFET, this is the typical process. But what happens? Oxide layer can be created by simply oxidizing the silicon. Okay, oxide SiO2 is there, right? I have a silicon substrate. If I will oxidize the layer, so I can create the SiO2. Okay, so the oxidation can be done with the two way. One is the wet oxidation, second one is the dry oxidation. Wet oxidation means with the help of some water molecule, I can oxidize and I will get, like, because there is H2O, okay, and with the help of that I can get SiO2 layer. There may be some possibility, like there is some, so what happens? If I am using the wet oxidation where water is there, and from the water I am getting some oxygen, but there is some hydrogen particles as well. Okay, so my objective is to create, this is the silicon substrate, this is the dielectric which I have created. This dielectric is nothing but this is the SiO2. I don't want any hydrogen pair with the silicon. I just wanted to pair the hydrogen silicon with the oxygen so that I can get the SiO2 for the oxide layer. Okay, and but in reality, it is not 100% true that you can avoid the hydrogen particles. Okay, so some of the silicon will be bounded with the hydrogen and they are very loosely bounded. This kind of bonds, we can call it the dangling bond. So with the small force, with the small energy, this dangling bond can break and they can change the threshold voltage of the device. So this is the thing which create a problem in the bias temperature instability. So ultimately, silicon and hydrogen used to bond and they are loosely bonded. With a small energy they can break, and because of that they can change the threshold voltage of a transistor with the time. So this silicon hydrogen bond, SiH bond, they break with the time, with the energy, how much load I am putting to that particular transistor, and because of that they increase the threshold voltage or the performance of the device with respect to time only, not at the same time or at the zero time. So this is the important thing that can be considered. Basically, there are two things in the BTI and that can affect both NMOS and the PMOS transistors, and we can call it the negative bias temperature instability and the positive bias temperature instability, and this both kind of instability can happen in both the devices, like in PMOS and the NMOS devices. So ultimately I will have four components: NBTI in PMOS, NBTI in NMOS, PBTI in PMOS and PBTI in NMOS. So out of these 4 components, NBTI in the PMOS transistor is more severe. Okay, that is more affected. That is more affecting the circuit performance. NBTI in PMOS. So this is really very important. Yeah. So NBTI becomes really very serious concern if the oxide thickness is reduced less than 2 nanometer. Okay. So yes. So one thing that is really very important that we can come up with this particular discussion. I just talked about if there is some break of SiH bond, that will lead to increase the threshold voltage. Okay. Now, if we can recall the previous things which we discussed about power dissipation, if the threshold voltage increases, what is happening? Threshold voltage increases means the power dissipation will reduce. Okay, and delay will increase. Okay. So now, if we can see here, bias temperature instability break the SiH bond with the time, which increase the threshold voltage, and by that we are getting 2 things. Yeah, this is because of the negative gate supply voltage and at the elevated temperature means at higher temperature. So what is happening? Yeah, this is nothing. I have already told you like what is happening here. So I can skip to this point. Yeah, this is important. Yeah, there are three effects that can be considered. The threshold voltage of the PMOS transistor increases. If the threshold voltage of PMOS transistor increases, that will reduce the leakage power. So now if you can recall, the leakage power is the major component that decides the power budget of that circuit. So if there is an effect of NBTI, leakage current will reduce, overall power dissipation will reduce. So ultimately what is happening? Might be this is one of the benefits that we are getting out of the bias temperature instability. So there are many research that has been done how I can utilize the bias temperature instability to my system, to my circuit more power efficient. So this is really very important. Like we are not losing everything, right? I am losing the performance, but I am gaining in terms of power. So because that is reducing the drain current. Okay, and the third one is speed degradation ultimately. So the system will be slow, your chip will be slower, but that will be more efficient, more power efficient. Okay, so if your objective is the power efficiency, then the BTI is one of the benefits. And if your objective is the performance, then BTI is the problem. So it's up to you, what is your application? And for what application you are developing your chip, you can decide whether BTI becomes benefit or it is the problem. Yeah, this is ultimately, initially this was the performance, it will change. Yeah, of course, I have already told you. If the performance, like it is taking this much of time, the lifetime of the circuit might be lifetime of circuit will be reduced because the delay has been increased. Yeah, this is shift in the current. Second and very important thing is, second reliability concern is, how much time I have? Accordingly, I can manage the things. How much? Huh? 10 minutes, right? Because I have taken too much time at the beginning. Okay, no problem. So I have 15 slides. Fine. The second problem is the hot carrier injection. What is this hot carrier injection? What happens? If I am applying some potential at the source and drain to operate this device, some of the charge at the lower technology, some of the charge particle may get accelerated energy and they start tunneling into the oxide. So this is one of the problem. So this is similar to the BTI, but BTI is due to the defects, due to the SiH bond breaking. They are increasing the threshold voltage, but in the HCI, the charge particle get accelerated, and because of that, they are tunneling into the oxide and they are increasing the threshold voltage. So ultimately, the outcome is same, but the phenomena is different. Okay, so the hot carrier injection is one of the reliability concern, and this happens especially if the thickness is less. Okay, so at the scale technology, the hot carrier injection is really very important concern, very important, serious concern that can be considered. One very important thing, if I am considering NBTI or the BTI affects when I am at a particular logic. Okay, but the hot carrier injection happens when there is a transition from 0 to 1 and 1 to 0. This is another difference between these two. So yeah, this is ultimately increasing the threshold voltage. Third one is the time dependent dielectric breakdown. What is happening? We know that dielectric strength, right? We have studied in the materials. And what is the dielectric strength? Dielectric strength indicates like how much maximum voltage a dielectric material can sustain without losing its property. Okay, that will act as a dielectric. But if I have increased the supply voltage, if I have increased the potential between the two terminals in the dielectric, might be it can lose its property and it start conducting. And this is what we have studied before. Similar kind of things can happen in the transistors as well. If I'm applying the large electric field, this kind of things we can call it the hard breakdown. But with the small electric field, initially this is the polysilicon, which is the gate terminal. This is the silicon substrate. This is the oxide. Initially I had these kind of defects, but with respect to time, more defects are generated in the oxide layer. And because of these defects, I can get some leaky path between the silicon and the polysilicon, and that can create a path between gate and the bulk. And it start losing its oxide property, oxide property. So this kind of failure, this kind of problem, we can call it the time-dependent dielectric breakdown. So time-dependent dielectric breakdown is because of defect generation in the oxide with respect to time. Okay, so this kind of problem we can call it the time-dependent dielectric breakdown. Yeah.
It means the silicon's particles are deposited in such a way that may make a path.
Yeah, so they are aligned in such a way they are creating a path between these two. So like this one. So initially they are randomly like this one. More defects are generating. They are creating a path between this and this, and we are getting some leaky path between these two. And because of that, there is no dielectric property. It loses. It becomes a conducting. So this happens because with respect to time actually. So this also decides when your system is going to be failed. So if there is more possibility of defect generation in the oxide, your system will be failed early. Okay, so I need to decide my oxide which is more reliable, okay, that can sustain for longer without generating too much defects. So this is one of the domain where people can think how I can come up with the oxide material that will have less generation of defects.
But by changing the thickness of the oxide layer,
but
control this.
Yeah, of course, but this will happen with the older technology. But if you want to miniaturize your device, you need to maintain the relation between the thickness of your source and drain depth. Equally, you need to reduce the oxide thickness as well. So if you reduce that one, this kind of problem will come. So at the lower technology, these are the problems. Because there is high probability that defect generation, like this leaky path, will be created early. But it's not like if I'm using the same material, then it will create a problem. But I need to use different kind of materials so that the probability of generation of defects will be less. So that can be postponed by this way. Yeah, so one thing, like we have seen two things. Some of the defects were like time dependent one and some were time independent one. Okay, so time dependent and time independent, spatial means time independent and temporal means time dependent one. If we try to embed these two things, this is nothing but we have seen, like if I have a process variability and I'm trying to draw a histogram or this Gaussian kind of pattern, if I'm trying to simulating any circuit at t is equal to 0, okay, t is equal to 0 means time independent one, I will get this kind of pattern which indicates what is the mean value of the delay and how much deviation it can have. So ultimately our objective is, if I am trying to design any circuit, or for delay performance, the mean value should be as small as possible and plus minus 3 sigma deviation should be as small as possible. Both things should be smaller. But if I am using like the same set of circuit after certain period of time, after including the temporal degradations, then might be the shift will be there in the histogram or in the variability. Because if you can recall, due to BTI, the threshold voltage was increasing, that was reducing the leakage power, but it was increasing the delay. So delay will increase means the mean value of that delay will be shift in the right direction. So this is the histogram, and this is simply a relation between temporal and the spatial, or the time zero or time dependent and time independent variability. So this is the relation. So ultimately, this reliability concern can create a problem in the distribution of delay. Okay, and might be at certain points it can start failing the things. Okay, so let us assume this is the distribution for delay, and this is the maximum limit which can our circuit can sustain. Okay, let us assume this one was the maximum limit. After this delay might be it is not meeting my delay specifications. Now this is the point. what will happen? If there is an effect of BTI or any temporal degradations, then my distribution will be shifted in the right direction. And if this will shift, might be up to this variation, it is perfectly fine, but these are some of the sample which will start failing. So some of the sample will fail, means might be your whole chip will not be useful, some of chip will be failed. So this information gives you the idea how I can check the temperature time dependency and how it can impact the performance of your circuit. So this is really very important, right? So BTI or all these like NBTI, SCI, TDDB and electromyogram, all these can lead to more failure probability. Yeah, these are some of the things that can be considered. With this, I will close it. So we started discussing about all these things, which are the NBTI, PBTI, SCI and TDBB. All these kind of phenomena can happen at the physical level, which is the silicon dioxide, SiO2 level. Okay, but if I have a single transistor, and these kind of effects can come at the device level, but they will influence the performance at different abstraction level. Because if there is some change in the performance parameter at the device or at the physics level, at the material level, if I am trying to design a device with the help of that one, this will impact in terms of threshold voltage, transconductance and the drain current. Okay, so at the device level, I will be able to measure the changes in the threshold voltage, will be able to measure the transconductance and will be able to measure the leakage current. But if I am using the same device, having the influence of NBTI and all those things, and I am trying to design the circuit, which is the inverter, in that case, I need to check, I don't need to check the threshold voltage. I need to check how much delay I have and how much power I have. Of course, I can check the trip point voltage as well, which is one of the threshold voltage parameter, but the major parameter for the gate level will be delay and the power. Okay, so it's not like whatever the effect at the device level will influence equally in all the abstraction level. That will impact, and it depends on what kind of things I'm going to make it. Similarly, if I'm using this kind of gate level, like logical gates to create certain circuits like SRAM. So in the SRAM, there are two things which are important. One is the static noise margin, and the second one is the critical charge. Okay, critical charge gives you the information about the software robustness. Okay, so at the critical charge, at the circuit level, I need to check the static noise margin and the critical charge. Ultimately, the origin of the difficulty, origin will be remain same, but the performance will be different. Similarly, at the system level, I need to check how much timing violation is there, how much data corruption possibilities are there. Data corruption means flipping the logic. Okay, because of the critical charge change I just talked about before. Like, so these are some of the outcomes at different abstraction level, but origin is remain same. Okay, so with this note, maybe I can close, because software I could not complete it because I was a bit slow in teaching. So,
Sir, can we focus on that reliability research changes?
Where? Yeah, of course, that is. So soft error, maybe quickly I can tell. So how much time I can take?
You can take, sir, please take.
Huh?
You can take 5 to
10 minutes, right? भूख नहीं लग रही आपको so कोई दिक्कत, फिर we can finish it, right? So quickly I will go through it, like what is the software mechanism, what happens in the software. So I think I have 10 slides. Okay, so out of 10 I will take 5. So what is the software mechanism? Software mechanisms means what happens if I'm using my chip for in the harsh environments, especially like nuclear environments or the space applications, where the probability of high energy particles are more, then those high energy particles can strike it into the sensitive node of the device, and they will create secondary electron hole pair in the bulk of the semiconductor, bulk of the MOSFET, and because of the secondary electron hole pair generation, they change its critical charge. Okay, so this is what is the major physics is happening in the devices, and because of that, might be there is a flipping of the logic from 0 to 1 or 1 to 0, depends on what kind of high energy particle is striking at the bulk. Okay, and because of this phenomena, if this is passing through a memory, so let us say I have memory, and that memory is storing logic 0, and if particle is strike at the sensitive node, then what will happen? If it is storing 1, might be it can flip 0, because I have a latch kind of things. So once latch is transferred, it will hold the same, the changed logic. It will change the logic ultimately. So these are certain problems that can create the problem. So the current injection that can be modeled with this one, which gives you double exponential current model to check the robustness against the soft error. Maybe I can tell you a little bit about this one. Let us assume what is happening here. Let us assume I have this circuit, and a simple circuit. I have this one, and I am considering at this node some transient impulse in generating because of the high energy particle strike. Okay, this is the particle strike, and the behavior of particle strike is nothing but they are similar to double exponential current. Okay, and if some particle strike is particle is striking at this node, and if it is passing through inverter, might be this particle strike having a sufficient amplitude that can be considered as a logic 0, a logic 1. And if it is passing through inverter, might be it can create an impulse like logic 0. In reality, we have not changed in the logic, but because of this particle strike at this node, it is generating a spike, and that spike can be considered as a impulse to inverter, and that can generate one negative pulse. And this negative pulse can change all this circuitry, and might be that can, even if the clock is enabled, then initially, ideally what I want to maintain logic 0 here. But this pulse can pass through this D flip-flop, and this D flip-flop can pass a logic 1. So, and then if I have a memory here, then what will happen? This 1 will be stored in the memory, and the whole logic will change. So a small particle strike at certain node can create a problem in logic flipping, logic changing. So this kind of problem, we can call it the soft error. So what to do? The thing is, we need to make these circuits in such a way which are more resilient to the particle strikes. And for that, what I need to do? I need to increase the critical charge of those nodes, which means they can store more high energy particle without flipping its logic. So this is one of the way that can be done. Similarly, this can happen in the timing violation as well. So I'm moving this one. But something can be masked. Yeah, these are some relation. Okay, I'm leaving it. These are some of the setup, like how to. So if someone are interested to do research in the soft error side or in radiation hardening side, it can be done in for both kind of circuitry, combinational as well as the sequential one. If I am talking about the combinational one, what I will do, because in the combinational one, there is no storage, there is no feedback path. Okay, so to check the soft error robustness in the combinational circuit, what I will do, I need to inject a current pulse of double exponential order at certain nodes, and I will check the change in the outputs and input behavior, and the point where it is touching, that will give you some critical charge information. And if I try to integrate this area from 0 to T critical for this current, that will give you the charge. So this charge gives you the information. Yeah, this is what is happening here. Like critical charge is nothing 0 to T critical, and if I am trying to integrating this current, that will give you the charge. And if this Q critical is higher, means you are designing more robust circuit which is tolerant to soft errors. So our objective should be how to increase this critical charge. So there are different ways to increase this critical charge, by increasing the node area, by increasing the current passing through it, current flowing through it, by increasing the strength of transistors. So these are some of the way how you can improve this critical charge. Okay. Similarly, for sequential, in the combinational, I need to check where they are touching to each other without flipping the logic, because there is no flipping possibility in the sequential, a combinational one, because there is no feedback kind of things. But in the sequential one, there are feedback, and there is a possibility of flipping the data. So for that purpose, what I will do, initially let us assume I have one node at VDD, one node at 0. If I have injected some current at some node, after a certain period of time, they will flip their logic. So it was 0, it will reach to 1, and it will reach to 0. So the point where both the voltage levels are crossing, that will give you the information about T critical, and after integrating this current, you can get the critical charge of the sequential memory, sequential circuits. The similar kind of phenomena can be happen. You can inject a current at certain nodes, because in the SRAM cell, here we have two storage nodes, Q and QB. You can inject the current at any node. So they will give you the flipped information. Okay. Yeah, these are certain challenges related to the reliability. As per the ITRS reports, there are two challenges. One is the near-term challenges, and the second one is the long-term reliability challenges that can be considered, especially for the semiconductor devices. The near-term challenges are, these are some of the near-term challenges, like you can talk about TDDB, NBTI, PBTI, random telegraph noise, hot carrier injection. So these all are the challenges for non-planar devices. As of now, lots of work has been done for the planar devices like MOSFETs and other things, but non-planar like cylindrical kind of tunnel FET and all those things. Still, there is a scope to investigate the effect of NBTI, PBTI, SCI, TDDB in those non-planar devices. So this work can be done. Second thing can be done, like how to avoid the gate to contact breakdown, which we are talking about TDDB. Okay, so by using the different kind of material as an oxide, you can avoid it. So what kind of material can be used without losing the performance? It's not like I will use this material and that will that will have a high dielectric strength, but might be that can lose your performance of the device. So we need to choose the oxide material wisely, which can give you the better performance in terms of TDDB without losing its property, like performance parameters. So this can be done. So here we need to come up with some different dielectric material for the MOSFETs. So here is one scope where people can work on. The second one can be like how you can increase the, similarly like statistical variation for non-planar devices. Because as of now, still non-planar devices are in research mode, not in the fabrication mode. Like yes, for testing purpose they have been fabricated, but not the commercially they have been used. So you need to check all these statistical and the temporal variation for non-planar devices. Similarly, it's not about a single device, because see, if we have some circuits, you have some devices, and to connect two devices, you must have some interconnects. So I'm talking about the reliability of individual devices, but what about those interconnects? So interconnects are equally important to check their reliability. So interconnect reliability is one of the concern where the people can think of. Okay, and yes, similarly, as of now, the device level investigation has been done. There are a lot of work that has been started in the circuit level, but still it is not mature. The people can check the reliability of circuits as well in more detail. Okay, so these are some near term, yeah, but the this is especially reliability of medical devices where the life involves. Okay, so that is really important, right? You need to check the reliability. That is why still the medical equipments are using older technology to make their electronic systems, because older technology are reliable enough as compared to the lower one. And if we talk about, let us assume I have an X-ray machine where I'm using some machine, some electronic system. X-ray may also impact the soft error that can create a problem, because I'm using the same chip in the same setup. Might be your X-ray machine may fail. So that is why the lower technology is not recommended, especially for the harsh environments. Okay, so the reliability for the critical applications need to be investigated, like medical, automotive, power grid, and all those things. If we talk about the long-term reliability issues, like which has been started, people need to work on this one. Still, the work has not been done, but it can be done, which will really create a problem, especially in terms of reliability. And those are the new material reliability, because see, every day people are coming with their new materials to design devices, but whether those new materials are reliable enough or not, they have tested that their functionality, like graphene and other things, carbon nanotubes, but whether these kind of materials are reliable enough for my applications or not, that has not been investigated. So the proper investigation is required of the new material being used for the new devices. And this is really one kind of challenge, research challenge in the near future that people can think of. Similarly, as of now, lots of research has been done on the device and the circuit level, but there is less work has been investigated at the system level. So system level reliability need to be investigated, that need to be checked. Similarly, muon induced soft error rate, they are similar kind of the especially in the harsh environments, having different property, like the weight of muon atoms are higher than the electrons and holes, and that may impact the performance of your circuit, especially in the harsh environments, because there is a high probability that we will get this kind of particle in the space, and they may impact the performance. So this is one of the things that can be considered. Thank you so much. So this is all about the reliability. One thing is missing. I was not able to connect the reliability and the security, because that is really very important. But yes, next time we'll see.
Sir, I have
Yeah,
one question.
yeah, fine, please.
For the photonics chip design, it is necessary to knowledge of CMOS technology for photonics chip design.
Basic fundamental, like ultimately what we need logics. Okay, so with photonics, like how much energy we have received and how much is it transmitting it. So it is not necessary. Device physics will be sufficient enough. Circuit is not required. So
Can you suggest some software available for the photonics chip design?
as of now, I don't have any knowledge, but because people have started. No, for the QC I was talking about.
Oh.
So there's a QCA Pro that can be downloaded freely, and people can start working on it. We have worked a lot. We have published lots of paper, and which is very easy to do that. So if you don't have any software resources available with you, you can start working from quantum.cellular automata, QCA. And this is really very good domain to work on. And of course, this is the future actually. So, and this is freely available, so you can use it.
Thank you.
Sir, one question is there. Sir, you in this starting slide you told that if one system is not reliable for particular.
Reliable, then you can use it for the security. Okay, so that is why I was talking about. I was not able to connect. Okay, I will connect it in 2 minutes. Any other questions? So I will come to that point last.
And then it is used for other systems. So can you give you some?
Yes. So let us assume. So this is really very good thing actually. So if we talk about circuit and system resilience, there are two things. One is the reliability, and the second one is the security. Okay. Reliability means we know that without failing the system, you need to maintain the performance. Okay. And security means you need to secure your data without losing, without hacking the things. Now what happens? You must have heard about the cryptography. Okay. In the cryptography, if you see your mobile in the WhatsApp chat, you can see that your message is encrypted. And what does it mean? Whatever the message you are transmitting, that has been encrypted with some secret key, and after encryption, that has been sent to the receiver and the recipient, and recipient will decrypt it, and it can see the information whatever you have sent. But there are three things involved. One thing is the information which you are typing, that your message. Second thing is the encryption process. Encryption process can be anything. Simplest encryption is the XORing the logic. And to encrypt, you need some secret key. So the question is how to generate this secret key. So let us assume I am designing a circuit which is not reliable. There is a high possibility of variability. High possibility of variability means random signal will be generated, random information will be generated. So those variability can be utilized to generate a secret key for the encryption purpose. So this is how unreliable things can be used to generate the secret key to make the secure systems. So this is some interconnects. There are many things that can be discussed here. There is one separate module on that, actually on security side as well, that can give you the bridge between reliability and security. So my team is working in both domains, like reliability and security. So if some of my circuit is not reliable enough, we used to shift into the security. So we are not wasting our idea actually. So this is what is happening.
Thank you, sir, for sharing the wonderful knowledge journey with us on reliability analysis of digital circuit design for reliabilities and hardware security primitives. Thank you.
Now, Kumar Yadav sir and Mrs. Smita Patil ma'am to honor our chief guest, Dr. Ambika Prasad Shah sir with token of remembrance.